Hello. The disembodied voice welcomed you to Fermilab. So for those of you who prefer, welcome to Fermilab. You get to make the choice. I'm out here to tell you about two programs that are coming up. One on quantum engineering. It's a lecture being given by Manu Oshalom from Stanford University, and it's just about sold out. So if you are a fan of quantum engineering, this is your chance. Also, the other program I wanted to tell you about is a radio theater presentation of It's Wonderful Life. Perfect for Christmas gifts. Bring people, give them tickets, December 16th. Now, we have a problem going on. We have incredible amounts of energy being generated by 5 teams of teens, and the lab has had to develop a special detector to handle the capacity of it. This is extraordinary what you're going to get. And in order to tell you all about it, you'll be hearing from Chris Miller, our MC of the night, whom I've been told I could introduce as a sweet young man from the College of DuPage. Now, there is a little risk of sexual harassment with that, but I'll take my chances. Chris Miller, you're on.
Hi. I love the compliment of a sweet young man. It's not true. Oh gosh, thank you. Welcome to Fermilab. My name is Chris Miller. During the day, I'm a professor of speech communication at College of DuPage, and in the evenings, particularly in the early days of November, I happen to turn into the MC of Fermilab's Physics Slam. And I just want to thank you for coming out. I mean, this is our 6th time doing this, and who's been here before? Has anyone seen a slam? So you know what's going on here. Look, so we just do, every time I come out, and I know I've said this in the past, I'm going to say it again, but this is the best show we've had. And it's not just the best show because I'm saying it. It's the best, well, okay, yes, it's true. It's because we're all here, and you'd be like, what? This is not the best show I've ever seen? That seems not worth my money. Look, this is an incredible show, and it's an incredible show for 2 reasons. Reason number 1, you may or may not be aware of this, but this is Fermilab's 50th year anniversary being open. Yeah, I mean, absolutely applaud that. 50 years, we have been blessed and honored to have this particular institution as part of our lives. It certainly changed Northern Illinois and DuPage County. But on top of that, it's not just more important, but equally as important that it being the 50th anniversary of Fermilab's opening. This also marks the 30th year anniversary of the opening of IMSA, which is the Illinois Math and Science Academy, absolutely, located in Aurora. Now, understand, I teach speech communication, right? So I'm backstage, and everyone is telling me about all the physics connection between Fermilab and IMSA, so I'm going to mess stuff up here, but I'm going to try my best. Here's the thing. From what I understand, IMSA and Fermilab have really strong connections. There's a lot of alumni from IMSA. A lot of people that come from IMSA come to Fermilab. In fact, let me ask this. Is there anyone in the audience right now that is an alumni of IMSA? Clap for me. Would you do that? By the way, this here is a fighter pilot, by the way, so keep that in mind. You might want to applaud for that person here in the front row. But we have an alum here, but we have more alum backstage too that are from IMSA. So this is a big deal because our presentation tonight, Physics Slam, is going to combine both IMSA and Fermilab together. We have 5 presentations, 5 students in particular from IMSA that are going to be talking about physics. Now, this is why I say it's the best show ever, because like you have seen me before, some of you have seen this before, you've seen me do it, and I'm not going to even try at all to make you believe that I know anything that's going on up here, right? I come and I watch the presentations to coach them, and I'm always, I sit there, row H is kind of like to go, and then they get finished, and I go, I think the content is good. I don't know. I have absolutely no idea what you have just said. But the cool thing is that I don't know what is going on. but by the end of the presentations, I do. And that's what's so great about these. And tonight, it's even more inspiring because they're students that are doing it. I mean, people that are young, under 18. And that is just, as a teacher, as an educator, that's inspiring. And in fact, I've always done this since I've been here. But let me ask you this. I want to just quickly, I want you to stand up. If you are under the age of 18, and you are here in the audience right now at Fermilab, getting ready to watch an hour worth of physics, stand up quickly, would you? Stand up. Yeah, see, that I like the most. This is why I do Fermilab. This is why I do the Physics Slam every year. Because I'm 44 years old, and I'm standing up here right now learning about physics. In the past, it's always been from people that are already doctors, have been practicing this for a while. But tonight, I'm learning from students. And even more than that, I stand up here as an educator, emotional. When I look and I see the people that are under the age of 18 standing up here tonight. I mean, let's think about this quickly. And parents, let's think about this too. These are people that are in the age of 18 that are on a Friday night, are here at 8 o'clock at night at Fermilab getting ready to watch stuff on physics. Yeah, that's some impressive stuff. And younger people, you know, the one thing I'll say to you is, the world seems scary, I guess, probably sometimes, just life in general, and people say stuff and do crazy things. Look, I looked at you guys as being my future. Honestly, the answers to what's going on in any of our problems lie here with you people that you understand what's going on up here behind us tonight. If you get this, please stay in it. Please stay in it. I mean, you know, it was funny. I was just the other day, I was saying to my son who's in the front row, he's trying to tie his shoes, and I said, Wyatt, just tie your shoes. It's not rocket science. This is rocket science. This is what I'm comparing him to. That's what I'm comparing tying shoes to. This is the night where we get to learn about rocket science. I thank you, people that are under the age of 18, thank you. Thank you. Didn't think I was going to cry tonight. But anyway, look, so I would like to be able to explain things about physics or explain things to you about these presentations behind me, but that'd be dumb. That'd just be naive. It'd be ignorant of me to try to do that. And in fact, that would just be selfish. Because in fact, I have maybe a new friend tonight, but I have a gentleman backstage. His name is Dr. Peter Dong. I keep wanting to call him Stephen, and it's just not what it is. Sorry, Dr. Dong, I apologize. He's back there laughing. But the point is, Dr. Dong is actually the professor. He's actually the teacher of the presentations that up here tonight. And I figured if he was here tonight, I was going to have him come out, let him tell you, give you some background, and tell you some great stories about some of these young people behind me. Because if they were my students, I'd be more than happy to tell you some funny stories. So he's got some things to say about them. And I'm going to pass this baton over to him tonight because this is his show. These are his students, and he knows more about this than I do. I'll be back here at the end, and I'll be more than happy to keep running this show. Before I introduce him, though, I want to lay down the ground rules for all of us. So just so you know how physics slams work. So this particular slam tonight, as all of them, each one of these speakers only gets 10 minutes. They get 10 minutes to tell you the stuff that they know about physics. And they can use anything that they want. They can do whatever they want. They can be creative. They can do lecture. They can whatever. You've seen it before. But the one rule is, well, there's going to be a victor tonight. And you're going to choose that through applause. All right? So the one only rule is that they can't go over 10 minutes. Now, in the front row here, we have a timer. So Dave is going to hold this in a second. If anybody happens to go over 10 minutes, you will hear this sound. Thank you, Dave. And that sound doesn't disqualify them by any stretch. But they did violate the rule that we have that's going at 10 minutes tops. So when we do applaud them at the end, you might want to take that into consideration. But I'm not telling you what to do. But just keep that in consideration. That's it. So anyway, I'm done talking to you. I'm just happy to see you again tonight. I will see you again. I'm hoping next year again. But tonight's the big night. And at this point, I'm going to turn this thing over to Dr. Peter Dong.
Okay, hi, thank you all for coming out tonight. My name's Peter Dong, and I am here basically because I have an IMSA ID and a Fermilab ID. So this is my claim to fame here. I am a teacher at IMSA, but I did my graduate work here at Fermilab, and I am now actually leading a student research group here. So it is very exciting to be here tonight. What we've done is we've paired each student with a Fermilab scientist. And they have prepared these presentations together, worked on them all together as a team. And so I'm going to introduce them to you one by one just so you have a feeling like you know them when they come on stage. So let's get started. Are you guys ready? Okay, that's what I like to hear. So tonight, our first presentations, starting with the Fermilab scientist. She is, I think, with no offense intended to anyone, the coolest person in this room because she has a license to operate a nuclear reactor. And that was when she was in college. She moved on from there to operate an even bigger, more dangerous machine, the Fermilab Tevatron. She spent 7 years working in the main control room of Fermilab. And let me tell you, when I was at the lab, I would read the main control room e-logs every day, and it sounds like the most exciting place on Earth. She's now moved on from there. She now runs the Gloomy cavern down in the neutrinos of the main injector experiment, and she's an engineering physicist. So those of you who don't know the difference between a physicist and an engineering physicist is that an engineering physicist actually does things. And physicists talk about it. As you can see, this is a scientist who clearly does not shrink back from any challenge, which makes her a good match for the student presenter we have tonight. This student presenter I know very well because she has taken a class with me a grand total of 4 different times, despite referring to my classes on different occasions as difficult, painful, torturous, sob-inducing, and hellish. And so what you can see from that is that she also is not someone to shrink back from any sort of challenge, and maybe is slightly a masochist. One of the most talented young ladies I've ever worked with, and a really impressive person, a debater, a writer, a chemist, a physicist, more than anything tonight. She pairs very well with the Fermilab scientist. So please tonight welcome our partners in physics, unafraid to shrink back from any challenge. Please welcome Fermilab scientist Cindy Jo and IMSA student Ganwadi Agrawal.
Excuse me.
You're excused. This is important.
Hey, I was working. Listen, if it's that important, I mean, this is my desk. You're gonna have to bring me in.
Okay. You want to help? Here, take this and fix the glitch.
What? How? Why?
It's simple. You see this yellow section? That's the glitch. It's blocking the signal. See if you can filter the data so we can use it.
Wonder what this signal is. Doesn't look too bad.
Come on, I need that ASAP.
Okay. Here.
Yes, it matches.
When did we get this data?
10 minutes ago. That's when the data was picked up by our Washington State detector. Nearly 2 seconds after they saw it, Fermi, the space telescope, saw a short gamma ray burst.
Gamma rays? Like the radiation?
Exactly. Really high energy radiation.
So what was that data I fixed? More gamma rays?
Nope. That was from our Louisiana detector. The second half to our Washington detector. Together, they form LIGO.
Hey, I thought you were supposed to be in a hurry. New data and all? Thanks to me.
We're still waiting. There's a data transfer issue from our third detector, Virgo, in Italy.
Well, while we're waiting, maybe you could tell me what this all-important signal is about.
I don't know. It's supposed to be secret.
Come on. I helped, didn't I?
Okay. It was a gravitational wave, probably from a binary neutron star merger.
Ah, yes. Of course.
You don't know what that is, do you?
Nope.
Let me explain. First, you have to understand something. you probably think that space is like this yardstick. It's rigid, and between this end and this end is always 36 inches. But really, space is like this bungee cord. Sure, it may appear a certain length now, but I can pull it and change its length. And this happens so smoothly that you couldn't tell if you were a tiny little bug living on the bungee cord. So things that have a lot of mass, like the Earth or a star, pull space, just like a person standing on a trampoline pulls and stretches the fabric. We call this pulling of space gravity.
I thought gravity was a force.
So did everyone else, until Einstein published his general theory of relativity. That's where all of this comes from.
Okay, so massive objects pull space like the sheet on a trampoline.
Right. And so if the person on the trampoline jumps, when they land, they pull the space even more, right? Or if they move, they pull the sheet in a different direction. That's what happens in space. So if I'm a star and I'm moving, I pull space as I move, and that changes the distance between the two marks on the bungee cord.
Oh, hey, and if you were to measure that distance, it'd look like a wave, getting longer, then shorter, and then longer again.
Right.
But I thought you said that you couldn't tell if the distance was changing if you were a tiny little bug and you lived on the bungee cord like we do in real life. So how do we measure it?
Like so. So let's say because of the Earth and the Sun, all the other nearby massive things, that the distance on the bungee cord is this long, the same as the yardstick. So let's put the yardstick right here, so it makes a nice right corner. Now, if there's something big that's moving over here, again, it's going to pull space in this direction, and now the bungee cord is longer than the yardstick. Now imagine if I were to send something along both the bungee cord and the yardstick, starting at one of these marks at the same speed. It would take longer to get to the opposite end of the bungee cord because the bungee cord is longer now, right? That's how we detect gravitational waves. We build a detector with two arms, positioned just like the bungee cord and the yardstick, and we send light down both of them. Light always has the same speed, so if it goes out at the same time, it should come back simultaneously as well. But when there's a gravitational wave, just like with the bungee cord, one of the arms gets stretched, and so it won't come back at the same time. So when we measure the time it takes for light to get back to us, we'll either find it was the same for both arms, meaning no stretching, no gravitational wave, or one of the trips took more time. There was a gravitational wave. You have to remember, though, that the change in distance from a gravitational wave is so small that we need really massive objects like neutron stars or black holes interacting to get waves big enough for us to study. You know, a neutron star, despite only being the size of a city, is so dense that 1 teaspoonful of it weighs 1 billion tons with a B.
Wow, I had no idea. That's really cool.
It's here, the data from Virgo.
Oh my gosh, bring it up. There's nothing. Does that mean LIGO was wrong?
No, there has to be a logical explanation.
You know, when you were explaining the detectors, it seemed to me that it couldn't always detect the waves.
I'd love to answer your questions, but I'm a bit busy right now trying to figure this out.
No, wait. The detectors are sensitive to the arms stretching different amounts, right? So if the wave came from this direction, wouldn't both arms stretch equally, and then you wouldn't get a signal?
That's right. You solved it.
Yeah, guess I did, didn't I? Kind of sucks that Virgil didn't see it.
Virgo, and it doesn't. Don't you see? Like you said, there's only so many directions it could have come from to miss Virgo but hit LIGO. Now we can locate it. Alert the astronomers. Every telescope should be pointed at the sky.
Now everyone, we're gonna need all your help as we look for the discovery. So please stand up. Come on, quick. We're on a timer here. Now, you might not know it yet, but you, as the audience, represent the night sky. Okay, so our gamma ray detectors, Fermi and Integral, helped us narrow it down to this part of the sky. So the rest of you can sit down. Now our gravitational wave detectors LIGO and Virgo were able to narrow it down to this part of the sky. So the rest of you can sit down. Finally,
Guys,
our optical telescopes were able to look at all the candidate galaxies in this region. I hope you guys are okay with being galaxies, because that's what you are. And finally, we're able to locate the binary star merger in the form of a kilonova. All right, we've made the discovery. Thank you. Please give yourselves a round of applause, and you can all sit down again.
There's so much to observe. Quick, note down my observations.
All right.
Day 2, August 18th. I see UV light, visible light, and infrared light. No X-ray or radio. Day 7th, August 24th. The UV light has faded, but visible and infrared remain. Still no X-ray. Day 9, August 26th. X-rays appeared. Day 13th, August 30th. Visible has faded, but infrared and X-ray still remain. Day 16th, September 2nd. The radio waves have been spotted. Finally.
Wow. Can't believe we got so much data just from one event. We're going to be busy for months working through all of this. Was it just me, or were the X-rays kind of late to the party? Not as late as those radio waves, though. I mean, 16 days. They get stuck in traffic coming back from the solar eclipse, too.
I don't really know why they were so late.
But I thought that the supernova was supposed to give us all those answers.
Kilonova, and that'd be boring. Think about everything we have to learn. We can measure how fast the universe is expanding. We can see what elements are produced in the explosion and what that might tell us about where we came from. Who knows what this radio wave and X-ray problem of yours might bring up?
But wasn't the discovery itself exciting enough?
It was. This is a once-in-a-lifetime opportunity. LIGO just won the Nobel Prize when they saw 2 black holes merging. But because black holes absorb all the light, that's all they saw. This time with 2 stars merging, we had light and X-rays and gamma rays and all other kinds of information. It's a whole new way to see the universe. Never before in the history of our world have we had access to this kind of information. It's blown the field of astronomy wide open.
Wow, and to think that all of this happened 130 million years ago and so far away that we're just seeing it just now. I mean, the dinosaurs only died out 65 million years ago, so that light is older than a T-Rex.
You're right, and it's still telling us so much. The stars that we saw might have danced and collided and died now, far, far away, but we still heard them. And now that we know how to listen, we can learn so much about our world from them.
Okay, and as you can see, we're off to a great start here tonight. So, for our second presenters, the scientist we have presenting tonight, he knows so much about particle physics, he wrote the book on particle physics. Actually, he wrote like 5 of them. He has also done magazine articles, journal articles, even his own YouTube channel. In addition, he has been featured in a bunch of things, and he has been a whole bunch of active physics discoveries. In fact, his name is on the 2 biggest particle physics discoveries of the last several decades, the top quark discovery in 1995 and the Higgs boson discovery in 2012. And so this man knows more about particle physics than just about anyone. Unfortunately, he is not able to be with us tonight for reasons you will discover shortly. So instead, he has found an associate of his who owes him a favor, and he has sent him in his place. So tonight, you will see you will not be able to see him in person, but you will see the work that he came up with. More on that in a moment. First, let me talk about the student presenter we have tonight, who is a very passionate person. Let me explain. You know, there's that famous study that showed that a majority of Americans are more afraid of public speaking than they are afraid of death. Well, this next presenter actually listed public speaking as one of his hobbies. He has a lot of hobbies that are sort of things that you don't normally see. Like one of his hobbies he listed was facilitating discussions about leadership. Among other things, he likes to exemplify and advertise Indian culture, of which he is a proud ambassador. And he has this thing about radiation shielding. Let me tell you about radiation shielding. We had this project in modern physics. It wasn't meant to be that big a project. It was about radiation shielding. This guy just kind of got into it and developed this kind of lifelong love affair with radiation shielding. You cannot get him to stop about radiation shielding. And I haven't had the heart to tell him that radiation shielding is like the most boring topic in physics. And it's the thing that we give to the first-year grad students because no one else wants to do it. But I would say if you can get passionate about radiation shielding, you can be passionate about anything. Tonight we can see him using his passion both for public speaking and for physics combined to show you this presentation brought to you by the dynamic duo of Fermilab scientist Don Lincoln and IMSA student Abudaya Bala.
Oh my goodness. What are you doing here? What am I doing here? Oh, yeah, it's the Fermi Physics Slam! Wait, I'm on this side of the stage, which means I have to give a talk. I only have 10 minutes. Don's not even here. I have the perfect thing. There we go. All right, let's try this again. Hey, audience, so I'm going to tell you about quantum computing. It's the coolest. Wait, you didn't even know about quantum mechanics, do you? All right, so we'll start from quantum mechanics. Huh? Oh my goodness. Are you Albert Einstein?
Yeah, it's me.
What are you doing here?
Well, where am I now? Or rather, when am I now? I've been time traveling, you see. A famous physicist named Don Lincoln from someplace called Fermilab invented a time machine and took me with him to see the world. Unfortunately, he stepped back into that machine by himself, and he's now disappeared. And I have no idea where or when he is.
You know, that does explain a lot. Anyway, how do you like my time?
I like this time very much. Physics has come so far. Yeah? There are these wonderful devices I've discovered that fit in your pocket. It's fantastic. Yeah, you can make a telephone call on them. You can read a book on them. You can even watch a movie on them. Have you seen the cat videos? I love the cat videos. Would you like to watch one?
I've seen plenty of cat videos on the internet, thank you. But I'm really glad you like my time.
Yeah, me too. I thought the world would be a lot stupider by now, but I was wrong. Anyway, what are you working on now?
Oh, I was just going to talk about quantum mechanics.
Quantum mechanics, it's all bunk. I was talking about it just the other day to my friend Niels Bohr.
Well, wait, Albert. There's no need to give our audience the wrong impression about quantum mechanics. Why don't we let them decide for themselves whether they like it or not?
Fine, but they must understand it already.
Albert, not all of us have Nobel Prizes or some sort of geniuses. It takes time to understand these things.
But they don't look unintelligent. What are you, Packers fans?
Albert, just give me a couple minutes to explain it to them. Go have a seat. I don't want you interrupting me at all. Just give me a couple minutes.
Okay.
All right, quantum mechanics. So our world is made up of very, very tiny things, and they're governed by the laws of quantum mechanics. Now, when most people think of quantum, they think about the atom. So why not start there? By the way, you shouldn't believe everything that they tell you. They make up everything. Tough crowd. Okay. So the easiest way to visualize the atom would be like our solar system. A neutron star, electron planets. Looks pretty and cute, doesn't it? Kind of fits with the whole, our solar system looks like this, so tiny, tiny particles should be like this too. But that's actually not the case. In the quantum world, electrons aren't fixed to being at one place. They can be everywhere. Okay, well that's a bit of a stretch. Not everywhere, but they can be in a range. Think of it as a cloud. So where you have the nucleus, and then the cloud represents the range under which the electron can be in. But when we detect the electron, we find that it is in one place at some times, but not in others. Now, this is a bizarre phenomenon because electrons are both particles and waves. Well, what do I mean by that? Well, this was first discovered in the earliest 20th century when scientists threw electrons at two slits. Now, to determine whether an electron is a particle or a wave, you'd see how it results. So, if it's a wave, then the electrons would interfere with each other, causing an interference pattern, which you would notice on the back panel. But if they were particles, then they would hit one at a time, kind of like this. Now, when the actual experiment was conducted, it looked something more like this, where the electrons interfered with one another, causing an interference pattern, which showed up on the back panel. Well, great! Electrons are waves! But it's not that simple. The quantum world is much weirder than that. Let's take one electron at a time. Throw one, throw two, throw three. And they seem to behave like particles, hitting one at a time. Now, repeat it. Do it again, and again, and again. And once you look at bunches of electrons, you notice that it still creates an interference pattern like waves. This is so weird. Electrons behave like particles, but travel like waves. Now, this is the core of quantum mechanics. And even Schrödinger said,
Listen, don't get me started about Schrödinger. That guy has like 50 cats.
Albert, what did I say about interrupting? Okay, Schrödinger. So Schrödinger and his cat, his one cat, placed it inside of a box, along with a radioactive substance and a Geiger counter to measure the radioactivity. Now, once the radioactivity reached a certain level, it would release a hammer, breaking a vial containing poison, thus killing the cat. Sad. Now, let's close the box. To you, to me, to the rest of the world. The answer lies once we open the box. But in the quantum world, it's both dead and alive.
I understand this, but I don't like it. The universe is not random. I've said it before, God does not go around throwing dice left and right. There's a cause for everything.
But we've proved this to be real. It's not some sort of theoretical daydream. It has real utility. You can even use it in cryptography.
Cryptography? What kind of cryptography?
Okay. So cryptography is essentially the science of obscuring a message just so that only the intended reader can read it. Now, this is used all the time. Even when you're buying candy off of the internet and you put in your credit card number gets encrypted so that hackers don't steal it. And the modern day encryption system is known as RSA. So, how does RSA work? RSA works when you take two primes. Everyone remember what a prime number is? 2, 3, 5, 7, 9? Gotcha. Good job. Wow. Well, you take two prime numbers, two very large prime numbers, multiply them together, and you get the encryption key. Now, in order to decrypt, you need the two initial prime multiples, factors. Now, let's try it out. So, how much do you remember prime numbers? Factorization of 21. 3 and 7. You guys are really smart. Try this one. 28,891. Without using your phones. Good guess. 167 by 173. Now, there's a real hidden gem in the audience. You should probably stand up. I'm pretty sure Fermilab will hire you. 165,049,530,853. 15,487,429 by 10,657. Now, it's a little hard to try and factorize larger numbers like this. But all of these numbers can be easily factorized by computers today, which is why modern day RSA encryption keys look more like this. Try factorizing that. Now, The modern computer, to factorize this, would take years. Well, it wouldn't take years if you're using a quantum computer. Now, a quantum computer would be able to solve this within a day. How is that so? Well, the modern day computer uses bits, where everything is zeros or ones. In quantum computers, use qubits, which can hold multiple states simultaneously, zeros and ones. And this is what gives them the efficiency and the power to be able to crack this in less than a day. Now, I know what you're thinking. It's kind of scary. But quantum computing also comes with encryption, where it's safe from its own decryption methods and can even let you know whether your message has been intercepted or not. So this is why we need to push for quantum computing and quantum cryptography. It's essential. I guess you could say it's the key to the future. So that, my dear friend Albert, is why quantum cryptography is useful.
Well,
Am I right, audience?
Well, now you've made me very, very nervous, and I must go.
Where are you going?
Where am I going? I'm going to change all my passwords.
Thank you so much.
Okay, so I didn't have a chance to say it before so as not to spoil the surprise, but Dr. Lincoln actually wasn't here tonight, so if we could please give a warm hand in recognition of his substitute, who was another Fermilab scientist, Bill Freeman. Our next scientist presenter tonight works at Fermilab, but really just as a moonlighter. Because he also is the head of a band that has recorded 3 albums, and he's performed for more than 10,000 people at a time before. And so he basically just does physics on the side. So as a side job, he is a professor at University of Chicago with a joint appointment here at Fermilab. The sort of thing he works with is dark matter and cosmology. So he works with stars and galaxies and a lot of things that are very bright and energetic, which makes him a perfect match for his partner presenter tonight. Okay, when I teach our modern physics class, at the end I like to give a little talk talking about why we study particle physics and why it's worthwhile doing, even though it's not like biology where it seems like it's really helping people, why it's still worth studying. And at the end of it, most students are like, oh, okay, that's nice. But one student stood up and said, "Take that, biology!" To say that this next presenter is passionate about physics doesn't really do her justice. I think if she could, she would change the laws of the state of Illinois to allow her to legally marry physics. If physics were a princess, she would be its knight in shining armor. If physics were an author, she would be its agent. If physics were a country, she would be its entire nuclear arsenal. And so with both such people so full of energy and full of excitement about physics, I invite you to welcome to our next presentations from Fermilab scientist Don Hooper and IMSA student Isabella Gannett.
Good evening. Today I'm going to tell you about the particle known as the muon. The muon is a lot like the more familiar electron, but it's about 200 times heavier, and it decays in only 2.2 millionths of a second. Along with the electron and muon, the tau collectively make up what are known as the charged leptons. The charged leptons are 3 of the particles that make up together the standard model of particle physics. So in short, the muon is a lot like the other charged leptons. And the charged leptons are really not that different from the other 17 particles in the standard model. There's nothing really special about the muon.
Wait. Professor Hooper, you've got it all wrong. Muons are like the bestest particles in the history of ever.
Isabella, what are you even doing here? And more to the point, what are you doing in that ridiculous costume?
Well, I'm wearing it in honor of my favorite particle, the muon. Ka-chow. Nailed it.
If it were up to me, puns would be outlawed, but moving on. What is so different about the muon? What makes it so special compared to the other elementary particles?
Well, let's start off by comparing it to the boring old electron. The muon is about 200 times more massive, and it decays about 2.2 microseconds. That makes it useful in all sorts of different ways.
Really? Like what kind of ways?
Well, did you know that the muons are being used to scan the pyramids of Giza?
I did not know that.
The technique is called muon tomography, and it can scan for hidden burial chambers deep within the pyramids, things that we didn't even know about. The project started in 2015, and it already has results. It's been all over the news.
Okay, that's pretty cool. I'll give you that.
And then there's the G-2 experiment here at Fermilab, and I work on it, by the way. So how it works is that muons are charged particles, and once they're in magnetic fields, they spin. So all sorts of different particles can impact how a muon spins, including exotic particles that we don't even know about yet. Has anyone here heard of a theory called supersymmetry? All right. Could be better. But physicists feel that supersymmetric particles also impact how a muon spins. So by running this experiment, we not only learn more about the muon, but also about these exotic particles. Take that.
All right, that's pretty cool.
But this is only the beginning. One day we'll be able to accelerate muons to enormous energies and smash them together with other particles, creating all sorts of new exotic matter. Muons are the future of high-energy physics. You know what? This calls for drastic measures. No matter who you are or where you came from, we can agree on two things. One, that the muon is like the bestest particle in the history of like ever. And two, that those electrons, those taus, those neutrinos, they just don't understand. Hit it. All right, everyone, let's start clapping. Get to the beat, come on. Let's go. The other Leptons are the same, no matter time nor space. They don't understand that the muon is without a doubt the greatest. To all the other muons all across the land, there's no need to argue. Leptons just don't understand. Keep clapping, come on, let's get into it. Let's go, here we go. In the 30s, accelerators were really non-existent. We didn't have the tech to create high-energy collisions. The sun radiates for days and days. It travels to the Earth. They're called cosmic rays. In 1936, two physicists answered the call to look at these rays and see if there's anything at all that could add to our understanding of our mighty universe. Their names were called the Anderson and Seth Nettermeyer. They did it. The duo had a new particle. They didn't know what it was, but it was kind of remarkable. It had the key properties of Yukawa's new meson. They named it the Mu meson, but that didn't last for long. Plot twist, it wasn't Yukawa's golden gem. All I could say to that is, well, rip them. It turns out Mu meson isn't even a meson. Sit down. You have a cousin named the Muon. Hacks yelled physicists around the world. Who ordered that? Rabbi yelled after he had heard. The best things in life come not when we expect it. And of particles, the Muon is, of course, the most legit. The muon is MIA, with neutrinos and others in the mainstream today. But let me tell you, the muon is mighty, mighty cool, with properties that make it an underrated jewel. The muon is an electron with a lot more mass. That means it decays really, really fast, 2.2 microseconds. That's how long it takes for a muon to come and then without a break. Although it decays, that doesn't hold the muon back. Time dilation is a mighty, mighty useful hack. It keeps it around for longer than we expected. Useful in ways that are unprecedented. In accelerators, the muon could be a sensation. With high mass, the muon has low synchrotron radiation, and the muon can be accelerated to high energies. Muons and accelerators have been counted. Keep it going. Everyone get involved. I want to see everyone clapping. Why isn't everyone clapping? And that's me, by the way. Okay, here's the situation. Muons are moving and, of course, precipitate, and they have charge. They couple to magnetic fields. But how do they couple? What does the G factor yield? Dirac said the G factor is simple. My equation is real quick and nimble. Mu equals G times E and S, then divide by 2M. Simple, yes. There's something I need to include. This equation only works with one particle in the room. If there are more, you gotta take them all into account. The calculations, oh boy, I wish you good luck. My equation says the G factor is 2 for the muon, but there are other particles too. Virtual particles and photons mess everything up. It means more math, but hey, that's what's up. Heck, said the theorist and experimentalist. We gotta calculate what G is. I'm just gonna make a long story short. The results didn't match
experiment in theory. Hacks said the theorist and experimentalist. Is the difference significant or not? Well, if it is, there might be something new. And that's the story of G minus 2. Then there's muon tomography. It's like a new kind of 3D photography. Muons can scan really big things, like the pyramids, to see what lies within. The project started in 2015, but now they got results so that we can see that there are more barrel chambers than we expected. But there is still more data to be collected. How does it work? Muons are everywhere. Cosmic rays produce them in the atmosphere. You just gotta put a detector close, measure density from how the substance is opposed. I know the pyramids are super cool, but tomography is a mighty useful tool. You can use it to scan all sorts of stuff, like active volcanoes. Yeah, sure enough, magma has a different density from the rock around it, so we can see where the magma is. And if it's close to the surface, we can send out a warning, a major public service so enclosing. Muons are the bestest of ever. We can use them in ways that are super clever. Scan the pyramids and volcanoes too. And right here at Fermi in G minus 2. So everyone out here in the crowd, sing the last line with me out loud. To all the other muons all across the land, take it from me, leptons just don't understand. Thank you, everybody, and remember, leptons just don't understand. Move.
So our next presenters. First, the Fermilab scientist is so good at what she does that when she joined her experiment, they named it after her. This next scientist, she works at the Minerva experiment on neutrinos, where she is making a lot of important discoveries about these really difficult to understand particles. She is here at Fermilab on a Wilson Fellowship, which I guess maybe you don't realize how important, impressive a Wilson Fellowship. But getting a Wilson Fellowship to a particle physicist is like getting into Harvard or something. Actually, it's better because no one ever gave me a Wilson Fellowship. So. She spends her time working with neutrinos, which are some of the most difficult, complicated, and puzzling particles there are, which is why we thought it would be a good idea to pair her with this IMSA student. Now, at times like these, it's good to remember that big discoveries in science aren't always made by people who are loud. Actually, a lot of the most important things that have happened in science have been made by people who are quiet, introverted, even shy. And so tonight's student presenter is totally not at all like that. He never stops talking. In fact, he'll talk about anything, but of all the things that he talks about, and he'll talk about, universal background checks for gun sales, and he'll talk about the customer service at Five Guys and one of his personal favorites. He'll talk about his grade in my class. But really, I don't think anything gets him as excited as talking about physics. This student is someone who really loves solving puzzles, and I think to him, physics is just like the world's biggest puzzle waiting for someone to take a crack at it. And I could think of no two people better suited for this challenge than these two rising stars in the constellation of young particle physicists. Please welcome our next presenters, Fermilab scientist Minerva Betancourt and IMSA student Manny Favela.
Hello, my name is Manuel Favela.
I'm Minerva Betancourt.
And our topic, if you haven't read the title slide yet, is on neutrinos, nature's transformers. But before we begin, we must first explain what a particle is. Particles are very, 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 very tiny bits of matter. They make up the entire universe. But just how small can particles be? Well, I like to make this comparison with fruit, the only time I actually use fruit in my everyday life. This is a grapefruit. Grapefruit has atoms. That's a fact. Like everything else in the universe, it has atoms, but just how small can the atoms be? Well, we need to increase the size up to actually see the atoms. So let's say we make this grapefruit the size of the Earth. How big would the atoms have to be in comparison? Well, we find that the atoms have to be the size of a blueberry. Just imagine how many blueberries it takes to fill up the Earth. That's how many atoms it takes to fill up a grapefruit. Crazy. But we're still not at the particle level yet. So let's take our blueberry atom and increase it the size of an Olympic racetrack. how big would the nucleus be? The answer? A little p. Now, I know the people in the back are probably thinking, Manny, why did you choose such small fruits? We can't see it. So please don't be offended. We have images up here for you all to see. So please don't feel left out, by all means. We want to include everyone here. But we're still not at the particle level just yet. So we have a p nucleus. We need to increase that to one more size of an Olympic racetrack to get the size of an electron, which is, drumroll, another p. So we go from the size of a grapefruit to the Earth to the size of an atom being a blueberry. Blow that up to the size of an Olympic racetrack, we get the nucleus of p. Blow that up to another racetrack, and we're finally at the particle level. It's crazy how tiny these particles are. But there's more to this field than just being tiny, otherwise this would be a lot shorter of a presentation. So there's different types of particles we can look at. There's quarks and leptons. Quarks are basically what make up protons and neutrons, and these are strong force, which, hence the name, is the strongest of all forces. Then there's the leptons, and that's where things get a little interesting. We get electrons, muons, and taus, and muons or taus are basically heavier and shorter-lived electrons. And what we see is that for each of these stages, there's a neutrino. So the neutrino, there are three different distinct states. There's an electron neutrino, a muon neutrino, and a tau neutrino for each one of these different leptons. But what's strange about the neutrino in comparison to any other state is that they use weak interactions. And weak, as the name suggests, is the weakest of all kind. How weak, you might ask? Well, if we had a light year of worth of iron and we just shot neutrinos through it, it would hardly be phased at all because the interactions are so weak and they happen so infrequently. It's very hard for physicists like Dr. Betancourt to actually see them. And so now she'll go more into how we actually detect them.
So where do neutrinos come from? Actually, sun produces them. About 100 trillion neutrinos pass through your body every second without interacting with any of the other particles of your body. So as you can see, these particles are actually very abundant. So then you may ask, what do we know about them? Actually, we don't know much. We don't know the mass. We don't know which one is the heaviest. We don't know if the neutrino is equal to the antineutrino. Manuel just told about 3 types. What about if there is another one? Some of these are the questions that we are trying to answer at the lab. Plus, neutrino could help to answer some of the biggest questions in the universe. Why in the universe we have more matter than antimatter. So I'm going to show you how we make neutrinos here at the lab. And actually, we have one of the most powerful neutrino beams in the world. So we basically, from an accelerator, we have our protons. We smash them into a graphite target. That produces charged particles, and that's what you see here. So some of them are pi plus, pi minus, neutrons. We don't care about the pi plus and minus. We just care about the pi plus to produce the neutrino. So we focus those charged particles with a magnetic field. So you see some of them goes here. We don't care about this. And then we have these that decay into a muon and a neutrino. So we don't care about the muons neither. So then we actually have a concrete block of steel there to stop the muons, and what we left is with a neutrino beam. So now we have the neutrinos. So how do we study them? We actually build huge detectors. So let me show you some examples. These are detectors that are running as we speak. So for example, we have Minerva, Nova, that are made of carbon. So you can see people here to give you a sense of the scale. And then we have the microboom. This is a new technology made of liquid argon. That is the technology that we are going to use in the future. So actually, we go from big to bigger to seriously big detector. And this is an example of the Nova experiment that is in Minnesota and is comparable with the size of an airplane. Now, Manuel is going to give you an example of what is that we see in these detectors. He's going to show you a neutrino interaction with a liquid argon detector.
So seeing the way these neutrinos interact with detectors is pretty cool. The neutrino will hopefully hit some of the atoms in the detector, and what we'll see is an interaction. This interaction produces a bunch of particles, protons, electrons, muons, and taus. And unlike neutrinos, thankfully, these don't use the weak force. And so with that, we can easily detect these types of particles, detect what type of particles they are, and from all these particles that are produced, we're able to retrace basically what happened, and able to tell what state the neutrino was in, whether it was electron, muon, or tau, and the momentum and energy of the neutrino, which is very crucial for us to have these experiments. With all these experiments going on, we found an interesting phenomenon with neutrinos that's quite unique compared to any other particle, and that is the idea of neutrino oscillations. Oscillations basically just mean change, although neutrino change does not sound as cool or scientific, so we say neutrino oscillations. What we see is that I originally said that there's 3 distinct types of neutrinos, electron, muon, and tau. But the thing was, I kind of lied a little. I'm sorry. They're not distinct. Each and every neutrino has components of all three parts. And so I like to compare neutrinos to transformers. So let's say for the copyright purposes, we have a neutrinotron. The neutrinotron is an automobile by day and a humanoid crime-fighting figure that protects the accelerators at night. And now what we can see is that no matter what state the transformer's in, it'll always have components of both parts. That is to say that when it's in its car figure, it'll still have the human head and the human arms. But when it's in its humanoid figure fighting crime, we see it still has the wheels and the car window shield of a car. So no matter what state it's in, it always has components of both. And that is true for neutrinos. It's almost like a slushy, really. If you have three different parts, electron, muon, and tau, you just put them all into one neutrino bucket. So you might have a little bit of electron and a little bit of tau and a lot of muon, meaning that the neutrino is a muon neutrino. But over time, what we see is that the shift can change. So the muon might decrease, the electron might increase, and now we see that the neutrino has transformed to an electron neutrino. What we see is that the probability of actually calculating how this happens is very difficult. You have to take a lot of factors into consideration. And so while hopefully I appear to be smart in front of all of you, I don't want to really tackle this math problem because it's way over my head. And we basically put this here to show you just how complicated this field can be. Well, we do like to make a lot of assumptions and make a lot of interesting discoveries to show you all how cool it can be. It really is one of the hardest fields in the world. And I want to show you all just how hard it takes and how smart people like Dr. Betancourt have to be to teamwork up and make discoveries like this in our everyday life.
So Manuel, let's give an example because just to make it simple. So you see this ball has two colors, so let's imagine the muon neutrino is the blue and the electron neutrino is the yellow. So I'm going to send some neutrinos from Fermilab to Minnesota, to Manuel. So are you ready to catch?
I'm not good at catching.
An oscillated neutrino?
Can we go back to the math equation?
No. Let's try this. We can do it. So
oh boy.
If he gets the yellow, it means that the neutrino oscillates. So.
Okay, here we go. Oh.
He got it!
You got it!
So this,
I'm not good at throwing either.
Often.
So what we see is with a bunch of our experiments, we actually see this idea of neutrino oscillations proven true. And we can see this with NOVA. NOVA has two detectors, as Dr. Betancourt said, one in Fermilab right when we make the neutrinos, and one a couple thousand miles away in Minnesota. When we look at the Fermilab data, we see a bunch of muon neutrinos, which makes sense because we can only make muon neutrinos as of this moment. But when we look at Minnesota, that's when things get interesting. We see a few electron neutrinos. Now, as all these neutrinos came from the beam, that means that some of the neutrinos inside the beam transform or oscillated into electron neutrinos, proving the idea of neutrino oscillations. So now that we caught you up to this fascinating world of neutrinos, where does the future lay? Well, we can see with the Deep Underground Neutrino Experiment, or DUNE for short, as every other physics experiment, we're pushing the boundaries of our knowledge and increasing our equipment to make us learn more about neutrinos. We're making the distance between these two detectors farther, so hopefully more oscillations occur. We're making the detectors bigger with liquid argon, which gives us more reliable and more accurate data. And we're making the neutrino beam bigger, so we have more interactions. This experiment will be released in 2024. So Dr. Betancourt, if you're looking for grad students, I'll be in the market then.
Okay, thank you.
What we can see is that we're hoping that this experiment will push our boundaries of neutrinos, just like many more to come. And we're hoping we can answer some of the biggest questions in the world of particle physics that Dr. Betancourt said, such as, is there another generation of neutrinos? Or is there another generation of leptons? What is the mass of neutrinos? We don't know that. We only know the change in mass between a muon and an electron. We don't know the exact mass. And for example, what is the idea of antimatter? We're hoping that with these experiments, we can learn more about this fascinating, cool, awesome, credible neutrinotron. And time.
So before we introduce our last presentation, I want to give one more word of recognition, and he won't let me do this while he's out here. So let me just tell you that all of these people have been working on this for a long time, and for the last 2 weeks, they've been practicing with a professional speech coach, who is none other than your MC. And so he's not out here right now, so I want to take the opportunity to recognize all the work that he's put in. Please give a hand for Professor Chris Miller. Okay, so for our last presentation, we paired these two together because they both do everything. So the Fermilab scientists that we are dealing with, he works on more experiments than I even thought was possible. He has actually worked on all 4 of the previous experiments described at this physics slam tonight. He's worked on microwave radiation, he's worked on muon G-2, he's worked on neutrinos, he's worked on quantum mechanics, he's worked on just about everything. More than I really thought was possible. In fact, it's like as if you'd gone to get a master's degree in biochemistry and then a PhD in history or something. He works on everything at once. So we thought it would be a great idea to pair him with this student, because this student is one of those people whose biggest problem is that he is too good at too many things. And so I think what he really wants to do in life is to be a physicist, computer scientist, a writer, and a pianist by day, and then by night, fight crime as a superhero. And you know what I think? Some people might call that unrealistic, but I say, you know, this world could use a few more physicists, computer scientists, writers, pianists, superheroes. And so I say, you go for it. Please welcome tonight. Actually, I should have said this earlier, but they've actually opted to have, they've worked on this together, but they're going to have only the student here on stage tonight. And I think when you see the presentation, you'll agree with me that that was a good move. So please welcome the presentation created by Fermilab scientist Chris Stoughton and IMSA student Rain Bravo.
Thank you for the kind introduction, Dr. Dong. Also, thank you for taking that away. I'm very excited and very happy to be here this evening. Every single person in this room and on this planet is an astronomer. I know that sounds absolutely insane, but I'm serious. You don't need a big telescope or fancy math equations to be an astronomer. Let me show you right now that each and every one of you is an astronomer. I want you to close your eyes and imagine the most beautiful sunrise you have ever seen. Go ahead, close them. I'll still be here. Imagine the sun peeking up over the horizon. You're on a beach. The clouds in the distance lit a soft gold. The sky gets brighter and brighter and brighter. Eyes open. Congratulations, that's observational astronomy. The sunrise is proof that things move around in the sky. You are an astronomer. Yes, you are an astronomer. So now let's do that thing astronomers love to do and start asking questions. First question, why does the sun rise and set? Well, I mean, we all know the answer to this one. The Earth spins on its axis. When it turns to face the sun, it appears to rise. When it turns away, it appears to set. But here's the kicker. Was it always like that? No. About 5 billion years ago, our solar system was just a big ball of dust and gas. The only reason that this big ball of dust and gas became everything we know is because of that same force that we all know and love. Gravity. Let's start with one hydrogen atom. That's me. Hi. Gravity pulls in another, then more and more. The gravitational pressure builds up until wham! Nuclear fusion happens. That's what powers our stars. And for the leftovers, well, they clump up around the star as big balls of rock and ice. The planets. Earth at one point was just a big ball of lava. Yes, when we were kids, we really did have it right. The floor was lava. But then it cooled, and well, here we are, the first sunrise. And man, getting this picture was a lot harder than you would think. Now, that's all well and good, but how does this story end? Well, spoiler alert, it's not pretty. In the future, the sun will expand, and the Earth and everything we know will be burnt to cinders. No more sunrises. Now, I know what you're thinking. Our sun is a backstabbing jerk. I mean, One day it's helping us grow our crops, supplement our energy grids, and get that smooth summer tan. The next, we're giving sunburn a whole new meaning. So why does it do that to us? Well, don't blame the sun. It's just following the laws of nature. In constellation, this expansion is very important for a future generation. This gas that it leaves behind will go on to form another star with another set of planets just like us. In fact, this future generation will need the remains of even heavier stars, whose cores can fuse carbon, nitrogen, and oxygen. And these heavier stars can leave behind neutron stars. And when they find their way to each other, they crash into each other, creating a kilonova. That's what LIGO saw last August. Astronomers pointed their telescopes up to that sector of the sky and saw that, yeah, this is how the universe was making its even heavier elements. I mean, this is how gold is made. So that answers our questions. We know why the sun rises and sets, where it came from, and where it's going. We even know where we came from. Stardust. We understand the sun. Really, we understand the stars. But there's something about all this that just bugs me. I mean, honestly, I feel a bit sad. It's not hard to feel a bit insignificant in the face of all that. I mean, we're like who's on a speck of pollen on a flower. Is this how Horton would see us? In space, we are on a tiny planet around a tiny star in an quality galaxy. Our local cluster isn't much to look at, and our supercluster isn't even that super. There are millions of galaxies in that night sky. The Sloan Great Wall, that slew of galaxies over our head, is over 1 billion light years wide. In the face of the universe, we are on a pale blue dot. I mean, we are, but on a pale blue dot. But we keep looking up. We keep making observations, coming up with new technology, coming up with new equations. We tease out the laws of nature. Why? Because it's what sets us apart. It's what makes us special. By knowing more, we become more. It's a bit like Pac-Man, but instead of dots and power pellets, we're talking data and equations. Figure out where the sun comes from, 100 points. Figure out where the planets come from, 100 points. Figure out where we come from, 100 points. I mean, that's why I love events like this, because we get to share in the riches of knowledge. In our first talk, we got to see what happens when stars collide and what that feels like to watch. 100 points. Thank you, Gunwadi. In our second talk, we got to see what's happening on the quantum level and how we're making use of it. 100 points. Thank you, Abu Daya. In our third talk, we got to see, well, what can I say? Leptons just don't understand. 100 points. Thank you, Isabella. In our fourth talk, we got to see how neutrinos change flavor and interact. 100 points. Thank you, Manny. Our minds have the power to know truth. Our minds have the power to know the truth. So hats off to the theoretical astrophysicists. Thank you to the observational astronomers who spend long, cold, dark nights in their observatories. Congratulations to the professionals who consume all of this and come up with new ways for us to learn even more about this. And where does that leave the rest of us? Well, we listen in on scientific talk, for one thing. Scientists and professors get really excited to talk universe with us. But, I mean, you saw Mandy's math equation. It's still really hard to understand. But that's okay, because we've got another way to embrace the universe. Artists, writers, musicians, they take that same universe and pass it on to us in another way. They touch our hearts. They reveal beauty. Our hearts have the power to love beauty. And we don't need equations for this one, because Our hearts have the power to love the universe. With the last amount of time I have left, instead of trying to dazzle you with one more equation or one more fantastic observation from the edge of the universe, I'd like to share in the other astronomical observation that we all share, the sunset. So once more, I'd like to invite you to close your eyes and imagine the sunset. There are no cat pictures this time. So go ahead, close them. I'll still be here. Do you see that ball of fire sinking into the ocean? The night critters starting to stir as the earth turns to slumber. With your eyes still closed, look up. The sky gets brighter and the stars glow. Aren't they beautiful? Van Gogh captures that starry, starry night. Frederic Chopin, in his Nocturne in C minor, takes the progression of night and turns it into sound. It's not gloomy, as it might sound. It's lyrical, hopeful. It captures the majesty of the stars, never losing sight of the sunrise. We can't all be Einstein, but we can know and love the universe just the way we are.
Okay. Well, if you ever are curious about, or if anyone ever says anything about the state of our youth today, you have a pretty good understanding that they might be beyond what we often hear. So how about one last round of applause for the people that you saw tonight, these students. And let me also welcome to the stage our co-MC for this evening, Dr. Tong. Dong, thank you so much for coming out here today. Didn't want to say Tong all the time. So Dr. Dong and I are going to go after we put the piano away, which was a surprise to everyone backstage, by the way. But once we put the piano away, we're going to vote, if you can actually help me out with that this evening. So what we're going to do is we're going to test this. Are we set up to test it right now? Okay, soon enough, as we get the screen up behind us. You're going to see behind us, it's whatever, rates, kind of, what's the word I'm looking for here, Dave? Decibels. That's why shouldn't be doing any of this. Okay, science! Speech is not working well. So here's the thing. So let's just assume for a second we're going to take me and Dr. Dong tonight, and we're going to take me first, and then we'll go to Dr. Dong, and just applaud, okay, in terms of, there's no better, because that wouldn't even be competition. We're just going to just see how this thing works, okay? So I'll raise my hand in the air for you to applaud. When I put it down, stop applauding, right? And we're going to see what the maximum score is for each of the presenters. So let's go with me first. Please applaud for Professor Christopher Miller. Okay, that wasn't great, but it was pretty good. Let's try this now. Okay, one more time here for my friend, Dr. Dong. Go. So what we got there is we'll get a max score, and we'll do that for all 5 of them, okay? So we're gonna go one at a time. If I may please invite all of our presenters out on stage with us, please. And since these are Dr. Dong's students, I will give him the liberty to introduce them one last time, please. Again, we'll just go with my signal. So once we start applauding, great. When I put it down, we'll finish then. All right, here we go, Dr. Dong. The floor is yours.
All right, let's just start on this side. So this is not the order they presented in, but I think you are smart people and can figure it out, right? Okay, so first let's hear it for the pair of Minerva Betancourt and Manny Favela.
Okay.
Next we have the pair of Cindy Joe and Gunwadi Agrawal. Next we have Don Lincoln, Bill Freeman, Albert Einstein, and Abuday Abala. Next, let's hear it for the pair of Dan Hooper and Isabella Gannett. And finally, last but not least, let's hear it for Chris Stoughton and Rain Bravo.
All right, excellent, and we will tabulate the results briefly. However, to the stage, we have a few prizes for everybody this evening, and we are going to invite to the stage to hand out these prizes. Do I see Dr. Lockyer here? Are you here? There he is right there. Everyone, please welcome to the stage the director of Fermilab, Dr. Nigel Lockyer.
Let me just say first that by switching out the order here, you've confused our people keeping the scores, so you got to give them a little extra time.
Dr. Lockyer, please take the stage and entertain us for 3 to 5 minutes.
What would you like to talk about?
I don't have any idea what to talk to you about.
Would you like to talk about physics?
I would love to talk to you about physics.
What's your favorite particle?
The Muon. Yeah. We do have some prizes to give everybody.
All right, let's just give everybody a prize.
Just, and just to keep you aware, after the show is over, we will be having a Q&A upstairs in the lobby with everybody, and there will be selling T-shirts for the 50th year of Fermilab's opening also in the lobby.
Are you a student?
I'm not a student.
No?
I'm not. That's very flattering.
Yes. Are you a student? I hope. Congratulations. There, you got a prize. Cindy, there you go. No. Student? Yes, okay, very good. Second student. Third student. Do you want one? Yes. Do you know what's in here? It's a Muon.
Right here.
Muon.
Yeah.
Student of life. Okay, here you go. Who's this for? Oh, scientist. All right, now the scientists get a present. Are you a scientist? Oh. You behave like one. Minerva. Cindy. Student. Hold on, Einstein. I'm not sure you're a scientist. Let's see. I've got 3 left. Yes, we do. Good enough for you. Scientist. All right. Scientist. Scientist. A hand for the scientist. Yeah. Okay. All right. So. More stuff?
More stuff.
What's this for? For the champion. Oh, for the champion. Hang on to it. Oh, we're going to do the champion now?
Yep.
Okay. Don't we do like last place first?
You're the director. You do whatever you want to do around here.
Would you like a notebook? Let's take some notes. All right. So, did the equipment work properly? It did? So who was the winner? Him? We're getting a little help. Could you just step forward, young man? Is this who you meant? Yay! There you go. Let's see, what are we going to do? Take his picture. Oh, he gets a sweatshirt? Or no, that's yours.
I don't know. That one's yours.
Oh, this is mine. Very good. No, this is yours. All right, here, shake your hand. Don't look at me. Look at the camera. All right, so who else we got? Jen, that's yours. And this is mine.
And as we pass them out, how about one more last round of applause for everybody that's up on the stage? And ladies and gentlemen, that does conclude this year's Physics Slam. We want to thank you for coming out. It's a lot less snowy than it was last year. We'll hope to see you again next year. Thanks for coming out. Appreciate it.
We are out. They will be available upstairs with the reception. Not having the formal Q&A today, so everybody upstairs, they're going to be answering questions. And there's T-shirts for sale up there, 50th anniversary T-shirts.